Hello, my name is Catalina Garcia, and this is my presentation on respiratory acidosis. So first, in this mini presentation, we will be going over respiratory acidosis, specifically what it is, what causes it, and then going into compensation for it. And then at the end, we will look at some research implications for respiratory acidosis. So going into this first, on this image, we have uncompensated and compensated respiratory acidosis. So respiratory acidosis occurs after an abnormal increase of carbon dioxide in our system. This is usually caused because of hypoventilation, which this causes the abnormal CO2 retention. Further, when abnormal amounts of carbon dioxide are lost through our lungs, this causes an increase of carbon dioxide and also generates hydrogen. So respiratory acidosis, in a general term, is the abnormal increase of carbon dioxide, mainly from hypoventilation, but can be caused from other reasons such as lung disease or depression of the respiratory center. This could be from drugs or disease. And then we also have nerve or muscle disorders that reduce respiratory muscle ability. So the ability for our lungs to function properly to expel carbon dioxide and intake oxygen. And then it can be caused by something as simple as holding your breath. So really what we're looking at is the retention of carbon dioxide, which causes an increase, a buildup of carbon dioxide, and then causes other effects. So in this image, we will be looking at the left side here, the uncompensated side. And in uncompensated respiratory acidosis, which is here on the left, carbon dioxide is elevated. Here in this example, it's doubled. And so bicarbonate is normal. So the ratio is 20:2 or 10:1 if you reduce it, and the pH is reduced. So therefore, what we see is an elevation in carbon dioxide brings a increase of hydrogen, but bicarbonate remains essentially normal. So in this image, we have both of the acid-base statuses shown mathematically, as well as within as a solution, mathematically as a solution of the Henderson-Hasselbalch equation. And then we have a visual representation of what is occurring in a balance beam or a seesaw that we see here. So where the beam tips down when the relative concentration of one of the sides of the seesaw increases. So, and then it tips up with the relative concentration of a member of the two on each side decreasing. So visually, we have our carbon dioxide and then our bicarbonate, and then we have mathematically what is occurring. So in respiratory acidosis, again, this is caused from an increase of carbon dioxide, an abnormal increase of carbon dioxide, which can be caused because of things as complex as lung disease to things as simple as holding your breath. So moving on. Okay. Now we have the compensation for respiratory acidosis. So compensation generally works to restore the pH to normal. As we can see in our uncompensated versus our compensated, we have our imbalance of our pH being 7.1. And then when we compensate for it, we're returning our pH to 7.4. Again, seeing here the visual representation of what is occurring versus the mathematical, which are saying the same things, just two different forms. So the way that our body compensates for respiratory acidosis is through a number of things. So in respiratory acidosis, a result is that bicarbonate stores in the body are elevated. In our example here that we see going into this, the plasma bicarbonate is doubled so that the bicarbonate carbon dioxide ratio is 40:2, as we see here, so 40:2. If you reduce this down, so 40:2 rather than the ratio here being 20:2. And so we don't want the 20-2 uncompensated ratio. What we're looking for is to have the ratio of 20-1, which is what our 40-2 ratio would be if you simplified it down, so that pH of 7.4 is achieved. So how the body is doing this is through various ways. So the first is through chemical buffers, which immediately are taking up additional hydrogen. The next way is through respiratory mechanisms. The next way, what can be failing, which we saw in our first slide, what can be failing is the lungs' efficiency so in nerve or muscle disorders that reduce respiratory muscle ability, so in the lungs' inability to expel carbon dioxide naturally, here we could see that respiratory mechanisms are not able to respond by just increasing ventilation, which would solve this issue, because in the event that it's our nerve or muscle damage that is causing the buildup of carbon dioxide or causing the respiratory acidosis, then we cannot count on our respiratory mechanisms to just increase ventilation, because this impaired mechanism, this impaired respiration is the problem. So the main factor in compensating for respiratory acidosis is through our kidneys. The kidneys are essential as they conserve all of the filtered bicarbonate and then the new bicarbonate to the plasma, as it also excretes more hydrogen. So again, this is what is happening organically, while here we can see visually and mathematically what the outcome is to restore our pH to normal. And this is by means of fixing the ratio from 20-2, 20 being our bicarbonate, 2 being our carbon dioxide, by doubling our bicarbonate to 40, so that the ratio, as you can see here visually, so that the ratio evens out. And then mathematically, we can see here how when you reduce 40-2 into 20-1, that's fixing our preferred ratio of bicarbonate to carbon dioxide. So these are the ways that our body will compensate for respiratory acidosis. The first way being through chemical buffers, and then essentially the most important way being through our kidneys, as they filter bicarbonate and new bicarbonate to the plasma as they secrete more hydrogen. So going into our research, from our researchers Gonzalez et al. From 2018, they looked at how the change in plasma bicarbonate concentration, change in arterial carbon dioxide tension, is a secondary response to chronic respiratory acidosis. So, and our bicarbonate concentration versus our change in arterial carbon dioxide tension, this secondary response is often not certain. So the response is not often weighed and stated. So the researchers looked at 28 outpatients that had chronic hypercapnia. These patients were studied, and they had found that those patients with steady state chronic hypercapnia maintained systemic acidity between the mid to main acidemia. So with this 95% prediction, it enabled differentiation between hypercapnia and simple chronic respiratory acidosis with additional acid-base disorders. So from our researchers, they sought out to look at the magnitude of the response of this bicarbonate to arterial carbon dioxide. And here we can see up here in these numbers, we have our 70 millimeter to our 0.48 in this slope that was created with a 95% prediction, differentiating between hypercapnia and simple chronic respiratory acidosis. So in a quick review, we look into respiratory acidosis, how this is generally caused from an increase in carbon dioxide, how hypoventilation is often the main cause, but can also be lung disease, depression of the respiratory center because of drugs or disease, holding our breath, or nerve and muscle disorders. We could see how the ratio of our uncompensated acid-base disorder is shown a 20-2 ratio of bicarbonate to carbon dioxide, where we want a 20-1 ratio, and this occurs through compensation by our body, such as through chemical buffers and the kidneys, generally increasing our bicarbonate so that the ratio shifts and our pH is compensated. It is restored. So again, this is, and here are my references. Again, this is respiratory acidosis, its general overview and research implications. My name is Catalina Garcia. Thank you.